Hey, General Chem 2 students, all you guys are awesome. Today we're going to do electrochemistry, and well, pretty straightforward. The first core set of equations, well, just one really for now, understanding cell potential. And basically, this is the voltage that goes across an electrochemical setup, and essentially the standard potential, which is represented by E naught for the entire cell, is going to be the standard potential for the reduction half reaction plus the standard reduction of the oxidation half reaction. Now, the reduction half reaction, that is essentially the half reaction where one component in your cell takes on or gains electrons, and that means it gains more negative charge or becomes less positive. And well, the oxidation half reaction is the exact opposite. That would be the component that during the reaction loses electrons or gives them away, thus becoming either more positive or less negative, however you want to look at it. Now, just for one example, this looks similar to like our Hess's law setup for Gibbs free energy, but it's actually going to be slightly different with how we change the numbers around. But for this particular setup, we're taking 2 moles of copper plus, copper 1 plus, and reacting it with a solid zinc to essentially form 2 moles of solid copper and zinc 2 plus ion. So effectively, the copper atom is going to be reduced because it's going to gain electrons, and the zinc atom is going to be oxidized or become more positive. So to calculate the standard cell potential for that entire setup, we're going to need to play around with our two half reactions. And the one that we do have is copper 1 plus, essentially reacting with one electron to form solid or neutral copper. And to basically represent this guy properly, we are gonna have to notice that our actual main reaction uses 2 moles of copper, or effectively, in order to keep the amount of electrons being transferred in and out the same, if our other reaction has 2 electrons, then we're going to need to times everything here by 2. So timesing this whole reaction by 2 just gives 2 moles of Cu1 plus and 2 moles of electrons being transferred to form 2 moles of copper, neutral copper. Now here's the thing. For Gibbs free energy or delta H or delta S, when we would multiply a reaction, we would also multiply the change in Gibbs free energy, change in enthalpy, things like that. For electrochemistry, we do not change the standard cell potential or the standard reduction potential for a reaction, for a half reaction, regardless of whether we multiply it by some coefficient or not. So even though, just to get things balanced, I multiplied the copper half reaction by 2, the standard cell reduction for that half reaction does not change. So just keep that number the same. Now, something that we are going to have to think about is the fact that for our second half reaction, this shows the reduction of zinc 2 plus to zinc, to solid neutral zinc. What we actually want is the opposite, so the oxidation of solid zinc to zinc 2 plus. And effectively, we could represent that by literally just turning this reaction around. And here's how this will look. Now let's get zinc up in front, solid zinc, right there. Boom, cool. Now here's the thing, we just flipped the reaction around, so we are no longer reducing zinc 2 plus, we are actually instead oxidizing it. So to better represent this equation, I'm just going to rewrite the standard half reaction potential for the zinc half reaction as an oxidation potential. And essentially the difference between a reduction and oxidation, or say if you flip a half reaction around, that merely flips the sign of the voltage or the potential. So in this case, we now have our two half reactions. They make sense because essentially for our copper half reaction, we are giving up 2 electrons, and for our zinc half reaction, we are gaining 2 electrons. So overall, 2 moles of electrons are being transferred. It's key that that amount of electrons being transferred is the same. Now, just to show that in a different slide, cool. We now have our standard reduction potential for our reduction half reaction of copper. And even though we multiplied everything by 2 in that half reaction, the standard reduction potential does not change in any way. You do not multiply the number. Now for the zinc half reaction, we took its reduction half reaction and flipped it around so that is actually an oxidation half reaction. And doing so essentially changes the potential for that half reaction. It changes the sign. So where it was originally negative 0.76, because we flipped it around, it's now positive 0.76. And essentially adding everything together, adding this entire reaction together, we're more or less going to cancel out those 2 electrons that are being transferred back and forth, or that are being transferred from copper 1 plus to zinc 2 plus, or to solid zinc. Effectively, those cancel out, and that gives us our main reaction, which again, of 2 moles of copper 1 plus and zinc to essentially transfer reactions forming 2 moles of copper and 1 mole of zinc 2 plus. Now to calculate the cell potential, or the standard potential of this entire setup, well, that's going to be straightforward. We are literally just going to add up these two half reactions. So effectively, if we have the first half reaction being positive 0.52 volts, and the second half reaction being positive 0.76 volts, adding those two together is going to give us a cell potential of positive 1.28 volts. And so cool. That is the simple way of calculating a standard cell potential. For this part, you can think of it like that Hess's law setup from prior. Just remember, multiplying by a coefficient, multiplying a half reaction by a coefficient, is just to get the same amount of electrons being transferred back and forth. But the coefficient that you multiply half reaction by does not in any way change the standard reduction potential. And if you flip a reaction, well, that just changes the standard reduction potential to a standard oxidation potential, which if the reduction was negative, then change the sign to positive, or vice versa. And then add everything together. Now, part 2 of our core equations. This involves the Nernst equation. This lets you determine the potential across an electrochemical cell when you're not at standard conditions. And the main kind of formula that you might see would be that regular or that non-standard condition potential equaling the standard potential of the entire cell minus 2.303 times the gas constant times temperature over N, which is the moles of electrons being transferred, and then Faraday's constant. And then multiplying that by the natural log of your reaction quotient. Now, we're not going to actually do equations. I'm not going to test you on this kind of formula. Instead, I'm just going to let you use the more simplified formula, which essentially goes like this. Say you're at a temperature of 298 Kelvin, so 25 degrees Celsius, standard conditions. The potential of that cell is going to equal the standard cell potential, so what we calculated prior, minus 0.0591 volts moles over N, N being the total amount of, N being the amount of moles of electrons being transferred, which in our sample problem would be 2 going in, 2 going out, so N would equal 2, multiplied by not natural log, but log base 10 of Q. So just worry about this bottom reaction or this bottom equation down here as far as answering questions for a test or for the extra credit. It's much more simpler, and that's all I need you guys to do. So continuing our sample problem with a copper 1 plus and zinc, let's calculate the potential for this setup. And the setup is an electrochemical cell potential is prepared with 10 molars of zinc 2 plus ion and 25 molar copper 1 plus ion. Determine the initial potential of the cell at 298 Kelvin. Well, for our reaction, essentially, let's look at it this way. Our main reaction, our total reaction, involves copper plus, which is aqueous, solid zinc, and then forming solid copper, and then zinc 2 plus, which is also aqueous. Well, that means that for our Q, since the reaction quotient never includes anything that's in the solid state, just things that are in a different state other than liquid water, that means that the only things we need to consider for our reaction quotient is the aqueous concentration of zinc 2 plus ion and the aqueous concentration of zinc 1 plus ion, which, according to the problem, zinc 2 plus is 10 molarity, and copper 1 plus has a molarity of 25. So that's how those numbers got plugged in. Now, since the stoichiometry is 2 moles of copper 1 plus, that's where this exponent came from, right down there. So don't forget that reaction quotients, dissociation constants, things like that, they do involve the stoichiometric coefficients, but as exponents. And for our reaction, for this particular reaction, it involved the transfer of 2 electrons. Therefore, what N would be down here is actually going to be 2 moles of electrons. It's not going to be 4, like 2 moles going in, 2 moles going out. It's just going to be the amount that was transferred. So that's why it's actually 2 and not 4 or whatever. Therefore, our reaction or our formula for determining the non-standard cell potential would be 1.28 volts minus the fraction of 0.0591 volt moles over 2 moles times log of 10 molar over 25 molars squared. Now, what that would end up being is this beauty right here, which says that the answer ends up being positive 1.33 volts. So the non-standard voltage still positive, and it actually increases from what the standard conditions was. Sometimes it can decrease, but whatever. Just know that the non-standard cell potential is positive 1.33. Now, our last set of core equations for electrochemistry, at least what we're going to cover in this class, is going to be relating it back to free energy. Free energy, which if it's negative, if the change is negative, then you know that that reaction can happen on its own naturally. And if the reaction yields a positive free energy, then in the case of electrochemistry, you had to force those electrons to be transferred instead of them transferring naturally. Now, for any calculation of delta G, it's simply going to equal negative NFE. Now, say you want to calculate the standard change in free energy, well then E would be the standard cell potential. Now, if you want to calculate like any other free energy when you're not at standard conditions, then you can calculate the regular cell potential and then plug that in. Now, for this equation, delta G equals negative times the moles of electrons being transferred times Faraday's constant times the cell potential. And to actually put that into practice, taking the same equation that we did prior, let's just plug in everything. So delta G is going to equal negative multiplied by the total amount of electrons being transferred, which in this case was 2. 2 went in, 2 went out, so 2. multiplied by Faraday's constant, which is 96,500 coulombs per mole. So that's going to allow moles to cancel out. And now we have 1.33 volts as our non-standard cell potential. We could have plugged in the 1.28 if we wanted to calculate the standard change in free energy, but that's not what's being asked for, since you don't see delta G naught. Now, plugging all those things in, essentially you're going to get delta G equaling negative 256,690 joules. Now, joules, that came from the fact that a coulomb times a volt equals 1 joule. So, coulomb volt, that's the same thing as a joule. Now, oftentimes since changes of free energies are huge, it's usually common just to actually simplify them into kilojoules. So 256,690 joules negative would equal negative 257 kilojoules. So either one, you could keep in joules or make it more pretty in kilojoules. I will likely not specify which I prefer, but kilojoules is cooler. Now, that essentially is it for electrochemistry, because those are the main equations you will actually see for an electrochemical setup. So, for extra credit this week, which will be due end of day Saturday, April 4th, here's the situation I'm giving you. An electrochemical setup is prepared with 40 molars of calcium 2+ and 16 molars of aluminum 3+ ion. Assume the cell is at 298 Kelvin during the entire reaction. So use that Nernst equation that uses a log of Q instead of natural log of Q. It's the second one, is much simpler. And the things I want you to determine is the standard cell potential, the non-standard cell potential at these reaction conditions, 40 molar calcium 2+ and 16 molar aluminum 3+, and then determine the non-standard change in free energy. So delta G, not delta G naught. And if it's all correct, plus 2 points. If it's mostly correct, plus 1. Now, here's the stuff that you will need. So the main reaction for that electrochemical setup will be 3 moles of Ca2+ reacting with 2 moles of aluminum solid to form 3 moles of solid calcium and 2 moles of aluminum 3+ ion. Down below are your half reactions where the reduction of calcium is a negative 2.76 volts and the reduction of aluminum ion is negative 1.66 volts. Just remember for the oxidation half reaction, flip it around and change the sign of the number. And for both of these, you're going to have to multiply the half reactions by some coefficient, because one involves the transfer of 2 electrons, one involves the transfer of 3. So hint, hint, you're going to want to multiply things so that you have a transfer of 6 electrons each, just so that the transfer of electrons is the same. And well, I guess just to reiterate, when you multiply the compounds or the elements in that half reaction, the coefficient you multiply by does not change the standard potential. So keep those numbers the same unless you need to flip the sign. And that's it for this week, guys. Electrochemistry, we don't need to beat the whatever the expression is, elongate it more than it has to be. So next Monday, you'll get access to your exam 3 and then the official practice exam or extra credit. And those will be due 2 Fridays afterwards. And then we'll do our last 2 lessons and get on to the last exam. And well, that's it, guys. Once again, it is a pleasure, even in this online format, to be teaching you guys awesome general chemistry. Have a great week, guys.